The purpose of this lab is to compare observed constant velocity motion with motion predicted by a model built on physics concepts. For the observed motion, I observed a tennis ball moving across my desk. Because we want to make a quantitative comparison of the observed motion with the motion predicted by the model, we need to be able to extract some numbers from the observed motion. In order to extract quantitative motion data from the motion that I observed, I needed only two things: a video camera, I used the video camera in my laptop, and tracker software. This is what the tracker screen looks like after I've imported the video and extracted the motion data. Because I wanted to capture only constant velocity motion, I had to exclude the first few frames and the last few frames from the video. The velocity is not constant in the first few frames because the ball is speeding up from rest. I also had to calibrate the distance by using a calibration stick, shown here. The positive x-axis is to the right of the origin, and the positive y-axis is above it. Here is our extracted data up close. The first column shows time. Each row of this column is increasing by 1/30th of a second. The second column shows the distance from the origin in meters along the x-axis. This measurement is in meters because of the magic of the calibration stick that I said earlier. Because of our convenient choice of coordinate system, we don't need the y distance in the third column. And here we have the motion of the ball frame by frame, with diamonds showing the center of the mass of the ball. Okay, at this point, we've quantified our observations, and now it's time to take that data and compare it with motion predicted by a model built on physics concepts. To construct our model, we need some physics concepts. Let's start with Newton's second law of motion. We can use Newton's second law to predict future velocity. In order to do this, we need initial velocity, we need to know the total net force from the surroundings, and the mass of the system, or in our case, the tennis ball, and the amount of time. Note that delta t must be small enough that F net remains relatively constant during the time interval. Being able to predict velocity doesn't give us everything we need in order to predict motion. We also need to be able to predict future position. We can predict future position, denoted by RF, if we know the initial position and the average velocity over a time interval that is small enough for the velocity to remain relatively constant. We now have two very powerful formulas that we can use to construct our model. Because F net can change, we want delta t to be very small. In our model, I will set delta t equal to 0.1 seconds. It took 7.33 seconds for the ball to travel across my desk, so we need to apply these formulas iteratively to get data points for the ball's position. First, we used Newton's second law to get the velocity after 0.1 seconds. Then we plug that value into the position formula to get the new position after 0.1 seconds. We repeat until the sum of those little delta t's is 7.33 seconds. The total time of the ball's journey across my desk. Note that in spite of all this talk about F net changing, F net doesn't change in our example. F net equals 0. However, we are constructing a model that is generic enough to handle more complicated motion, which we will encounter in future lab work. Computers are great at iteration, so the best way to apply our two formulas iteratively is to put them in a computer program. Here they are in a Python program. This line of code is just Newton's second law. It calculates a new velocity based on an old velocity and the other variables. And this line of code updates the position based on the velocity that we calculated in this line and the old position. Notice that all of this is happening inside a while loop. This means that the program is applying these two powerful formulas iteratively. The only remaining question is, where do we get these initial values from? The answer is that the initial values come from the observations of the tennis ball. I pasted the data from Tracker into a Google spreadsheet. You will notice that the spreadsheet shows a lot more precision than Tracker did. I didn't bother to round these numbers. I just took what I needed from the spreadsheet and pasted the values into the Python code. I'll start with the easy ones. The initial time is simply the first row comes from the first row in the time column, and the final time comes from the last row in the time column. And here they are in their code, the initial time and the final time. The initial position is also an easy one. It's just the first position in the position column. And here it is here. Recall that velocity is just the rate of change of position, which means the final position minus the initial position divided by the final time minus the initial time. We can use the first two rows of our data to get the initial velocity. In the second row, we have the final position, and on the first row, we have the initial position. Same thing with time. Next, we run the program to see if it runs as expected, and we see that it does. The motion looks similar to the motion of the tennis ball.